Okay guys, now remember that we previously discussed the resting potential, which was equal to minus 70 millivolts, and it was the potential difference between the intra and the extracellular medium when the neuron was at rest and it was not stimulated. And it was equal to minus 70 millivolts due to the presence of a high concentration of Na plus in the extracellular medium and high concentration of K plus in the intracellular medium. Now what if we stimulate this neuron by an electric stimulus? Will I still record a resting potential, or will the potential difference change? Now to understand this, we have the same setup as previously, but now we add two stimulating electrodes, S1 and S2. We have the recording electrode in the axon of the squid and the reference electrode in the extracellular medium connected to an oscilloscope. And then we will observe the following graph upon three different stimulations, S1, S2, S3, of increasing intensities, which means that S3 is greater than S2 greater than S1. What we will observe is the following. First of all, it was 0 millivolts. Why? Because the two electrodes, the reference electrode and the recording electrode, were in the same medium, and that means there was no potential difference. Then at the moment of insertion, I directly record minus 70 millivolts, which is the resting potential. Now, on S1 and S2, when I stimulated by S1 and S2, I just recorded a small artifact of stimulation, but nothing else. We maintain the resting potential at minus 70. However, when we stimulated by S3, and after a short delay of time, we call it the time of latency, the potential difference changes to plus 30, then to minus 90, and then goes back to minus 70. This is called the action potential. And it is the potential difference, the variation of the potential difference across the neural membrane when the neuron is effectively stimulated. And here we can deduce two important properties of a neuron. The first one is the property of excitability. It means that the neuron can be stimulated, can be excited by certain excitants. What are these excitants? The types of these excitants: electrical, chemical, thermal, mechanical, and light, depending on the type of the neuron. And second property, which is very important, is that we record it at a certain distance from the stimulating electrodes. And this is called the property of conductibility. To conduct, to transport the message from one place to another. So this is the other property of the neuron. Now also, we observed that when we stimulated by S1 and S2, we just recorded an artifact of stimulation and no action potential. Well, this happened because these two stimulations were below the threshold of excitation. They were low, ineffective. However, stimulation F was an effective stimulation because after a short delay of time, I record an action potential. So what are the phases of this action potential, and what are the ionic phenomena that take place along the neural membrane during this potential? Okay, now following the stimulus, this stimulus we said that should be above threshold. What does that mean? It means that it should open Na plus channels, which are voltage dependent channels. They depend on the variation of the voltage to open and close, to a certain number that increases the potential to minus 55 millivolts. Now, whenever we reach this potential, which is minus 55 millivolts, it means that we are above threshold and the action potential will be initiated. So we see that at the beginning, the opening of the Na plus channels allows the Na plus ions to go to the intracellular medium from the extracellular medium, and this will cause a depolarization wave for the potential difference to change from minus 70 to plus 30 millivolts. Now, why I'm using the term changes and not decreases or increases? Well, because you know that minus 70 millivolts as a value is less than plus 30 millivolts. However, as a potential, the potential difference as an absolute value was 70 millivolts, and now it is 30 millivolts. And this means that the potential difference has changed between or decreased between the intra and the extracellular medium. Now it decreased from 70 to 30, and that's why they use the term depolarization. Okay, we use the term depolarization because the potential difference, the difference in the potential as an absolute value has decreased from 70 millivolts to 30 millivolts. Although if we are talking about a graph analysis, you might say that it increases. We see that there is an increase in the variation. However, the polarity is decreasing, and that's why we use the term depolarization. Now, whenever we reach plus 30 millivolts, the Na plus gates would close and the K plus would open, allowing K plus to leave from the intra to the extracellular medium. And there is a delay in the closure of the K plus ions, so more K plus would leave to go to a repolarization because we bring it back to its initial value of minus 70 and continue the increase in the difference to reach minus 90 millivolts, which is called hyperpolarization. Now, as I said, hyper because as an absolute value, 90 millivolts is greater than 70 millivolts. Then the sodium-potassium pump would interfere, bringing back all the ions to their initial concentration, and the Na plus and the K plus ions would be closed, and we would go back to minus 70 millivolts. So in short, the action potential is made up of 3 or 4 different important phases. The first one is the depolarization, or also we call it hypopolarization. The Na plus enters through voltage dependent channels from the extra to the intracellular medium. Then repolarization, which goes from plus 30 to minus 70 millivolts, where K plus ions exit through voltage dependent channels from the intra to the extracellular medium. This is also followed by a hyperpolarization where K plus continues to exit, and then the pump would bring back the resting potential and all the ions would go back to their initial positions. Now here we can see the graph showing the variation of the potential and the variation of the number of open channels. Now we can see here the action potential goes from, they say minus 60 to minus 80. Okay, we talk about the average, which is minus 70. It goes to plus 30, then decreases back to minus 90 and goes back to its initial value. During this change, the Na plus ions, Na plus channels open first to reach 40 micrometers 40 channels per micrometer square, and then they decrease back to null after 2 milliseconds. And here we talk about the depolarization phase, and then the K plus starts to exit through the channels, and here we see the opening of the K plus channels. Look that they take a little more time to start increasing and they take more time to close, while the Na plus they open initially at the beginning. Okay, here we see that we have a resting phase. Then the Na plus ions enter through the open channels. The channel for Na plus closes and that for K plus opens, allowing the repolarization phase, and then a hyperpolarization where K plus continues to exit, and then the pump brings back the resting potential to its initial value at minus 70 millivolts.